Good morning, everyone, and I would like to thank the organizer for giving me the opportunity to talk. So I'll be presenting my work, which was done in collaboration with Shami and Manas, and which was recently published last year. And the paper title was "Spectral Properties of Disordered Interacting Non-Hermitian System." So I would like to start by explaining what is the disordered system. So the disordered system are the systems whose Hamiltonian or a dynamical generator has a term whose coefficient is random. And in the past, it has been studied that these systems have the, these systems have two various phases, which are known namely delocalized or chaotic, and the other one is localized. Since our system is interacting, uh, the localized phase is also known as many-body localized phase, and the connection of these phases exist from various conjectures with random matrix theory. So the delocalized phase, whose eigenvalue statistics corresponds to the random matrix statistics, while the many-body localized phase eigenvalue statistics correspond to independent random number statistics, whose distribution is known as Poisson distribution, depending on whether the spectrum is real or complex. So the one key feature which random matrix exhibit is that level repulsion. Level repulsion means that the eigenvalue tends to repel each other. And I'll be using this concept while explaining the certain things in the talk. So how does the non-hermiticity comes in the picture? Is that and when I refer to non-Hermitian Hamiltonian, it means that the Hamiltonian is not Hermitian. As a consequence, the spectrum of the Hamiltonian is complex. And actually in experiments, when one does the performs the experiment in controlled environment, what happens is that the interaction of the system with environment is inevitable. So due to these interactions, the system tends to dissipate. And to account for this dissipation, actually one needs to write an effective non-Hermitian Hamiltonian description for the system. And then that is the reason that we are studying this non-Hermitian effective description to actually conclude whether the system will be in delocalized phase or it will be in a many-body localized phase. So yeah, this is the representation of my systems we are using. So this red and green dots represents the on-site term. So this HI represents the on-site potential. So where HI is a disorder term, which is taken from a random uniform distribution of range minus h to h, where h represents the disorder strength. And this plus alternating sign of minus I gamma and plus I gamma represents the gain and loss happening at the adjacent sides. And this is the source of the non-hermiticity, where this the hopping is represented by the dark line on the ring, and there exists a nearest neighbor interactions. The first model has only the nearest neighbor hopping, while the second model has the long range hopping, which is shown by the dashed lines from within the long range connectivity is shown from this dashed line. So these are the two Hamiltonian which I just described. First one having only the nearest neighbor hopping, and the second one showing the long range hopping. So if you notice this alpha is the parameter which describes the range of the hopping actually. So if alpha is 0, then this hopping is equally likely for all from one side to any other side. And if alpha is increased, the range of the hopping reduces, and alpha tends to infinity corresponds to this Hamiltonian short range. So, and just one thing I think I forgot to mention was that the particles are hardcore bosons. So, and the spectrum of the system actually shows delocalized or chaotic phase for weak disorder, and that corresponds to non-Hermitian random matrices, and specifically it corresponds to AI dagger random matrix. While the many-body localized phase for the strong disorder corresponds to the independent complex random numbers statistics. So that's the description of the system. Yeah. So there are some specific to the simulation we did, that we actually work in the half-filling sector and exactly diagonalize the system numerically. So yeah, this is a just representative plot of the spectrums of the random matrix and the physical system. The top two plots represents that the spectrum of the AI dagger symmetry class. It seems like the spectrum of this first plot seems very uniform, and the second plot also. The difference of being, you can say that the shape is very different, but if I can carve out a disk out of the second plot, then it would be indistinguishable. So to distinguish between them, one needs to study the spectral statistics. And the lower down plot represents actually the spectrum of the Hamiltonian for the first model, for the weak disorder and the strong disorder. And as one can see that the spectrum of the first plot and the second plots are like, the first plot seems very homogeneous, while the second plot, the spectrum of the second plot shows that the system is the spectrum of the system is very inhomogeneous. So, but yeah, that's the reason one needs to study this systematically from the spectral properties. And one of the techniques to study is complex spacing ratio. So for the complex spacing ratio for any particular eigenvalue is defined as one needs to find the nearest neighbor of it and the next nearest neighbor of it with respect to the absolute distance in the complex plane. So, and the ratio is defined like this. So like a difference between the nearest neighbor eigenvalues and the next nearest neighbor, where the zk is the reference eigenvalue. And since this is a complex number, its magnitude is defined as rk and the argument is theta k. From the definition, it's clear that this rk will lie between 0 to 1. So as I mentioned, a level repulsion is something which is that the eigenvalues tend to repel each other. So from there, if the system is chaotic, then these two eigenvalues, this one and this one, don't want to be near each other. So hence, it's unlikely to find the rk to be very small. And similarly, if theta k is very small, then relatively these two eigenvalues, nearest neighbor and the next nearest neighbor, will be relatively close. And that's level repulsion prohibits that, or it's unlikely to find a small theta k, and if the system is chaotic. But if system is localized, or if they are uncorrelated, then it doesn't matter where the eigenvalues are, and the distribution of this zeta k is independent of the fact. So yeah, these are the plots for the first model, which was short range, only the nearest neighbor hopping. So I show the distribution of complex spacing ratio for the first model, and it shows like that the small r value is unlikely from the density, and the small theta k's are unlikely, and it shows an anisotropy in the distribution of complex spacing ratio in the complex plane. And this is actually the signature of chaos. Hence we claim that this is the delocalized phase, and this is for the weak disorder case. While this is the strong disorder case, and one finds that the spacing ratio is uniform. So how much time? So this is the distribution of complex spacing ratio here. And the second we actually look at is the marginal distribution of r and theta. As we increase the disorder strength, the marginal distribution of this r and theta goes from AI dagger class to a Poisson distribution, and that's just to show that that transition happens. And this is just another plot for this marginal distribution, showing the exact agreement between RMT only happens when we are in deep chaotic regime, which is 2 and 14. I mean, correspondingly localized. Yeah. So this is the second model where I was referring to the alpha. Yeah. So the alpha is the parameter which actually tunes the range of this. So alpha small means that it's a long range system, and also all-to-all coupling and hopping, sorry. And the alpha tends to infinity means only the short range hopping. So as one increases the alpha, the range of the hopping reduces, and so we actually, this plot shows the strong disorder case when H is 14, and we say that when the all-to-all hopping is possible, then even the strong disorder as H equals to 14 cannot localize the system, and we see a chaotic signature. And as alpha is increased, the chaotic signature disappear, and we see a localized signatures. And the same results are shown from the marginal distribution showing the transition as one increases the alpha. So my conclusions are that we established actually a correspondence bit of these gain loss Hamiltonian with the non-Hermitian random matrix AI dagger to be specific and demonstrate that transition happened from the diagnostic of complex spacing ratio. And with respect for first model, we tune the disorder strength, and for the second model, we increase the range of the decrease the range of the hopping to show that there exists a transition. And these agreements are only valid in the deep chaotic limit and the localized regime. So this was the one part of the work we did. The second part of the work, we actually looked at the dissipative spectral form factor, which actually calculates the long range correlation functions, long range 2-point correlation function for the same Hamiltonians, and we show the same conclusions actually. Yeah, thank you.
Let's thank Sparsh for the wonderful talk. So questions?
So just a couple of questions. So one, like when you had this alpha parameter, at what value of alpha you go from short range to long range, in the sense that which values of alpha you get the same results as the model one?
Yeah, we haven't looked at every value of alpha, but yes, like we have looked at 4 values of alpha. So I mean, yeah, 0, 0.5, 1.5, and 4. I would say, yeah, this 1.5 is still has some signatures of this, but yeah, alpha equals to 4 definitely seems to be a more, a more homogeneous distribution. So you could say somewhere between 1.5 and 4, I guess.
Okay, and the second thing, these distributions that you're showing about the complex spacing ratio,
right?
So this AA star, there is a specific prediction of the spread of eigenvalues, like what happens in the real random matrices, Hermitian random matrices. You have a bigness semicircle and so on.
Right.
Is there a specific prediction that you guys are matching to?
Yes, somewhat. Yes. Yeah. We have. Observed that this actually this was a 10,000 cross 10,000 matrix. So the spread is from 100 of radius n. So yeah, somewhat of a root n scaling we have seen the spread.
But is there a very explicit functional form that you can fit to?
That I am not really sure about.
Okay, thanks.
More questions?
Sorry, I just to clarify. So for the GIN-UE class, there are some analytical expressions. For the AI dagger class, I'm not so sure, but there's a lot of similarity. So there are minor differences, but you have some analytical handle. Yeah.
If there are no more questions, let's thank Sparsh again for the talk. Thank you.